Welcome back, Design Junkies. We're about to share some stress, fatigue the unfamiliar, and engineer your uncertainties into a master blueprint for a tranquil mind. Mechanical Engineering Made Simple starts now.
So I want you to picture a $500 million satellite.
Oh yeah, high stakes.
Right. It's packed with, like, the most sensitive optical sensors ever manufactured. It's sitting right on top of a launch vehicle. Engines ignite, and within, I don't know, maybe 40 seconds, the acoustic energy and the mechanical vibration of the launch just literally shatter the primary mirrors into dust.
Just completely turns them to powder.
Exactly. And that is what happens when someone gets today's topic wrong. Today, we aren't just looking at, idealized equations on a chalkboard. We are looking at how to mathematically predict, isolate, and actually survive mechanical shock and vibration.
Which is, frankly, the absolute enemy of structural integrity.
Yeah, so we've synthesized the core texts, the math, the field notes, really to build a framework for you. We're going from a simple single mass system all the way to a fully isolated 6-degree of freedom rigid body. Because the stakes are just incredibly high here. I mean, whether you are dealing with a spacecraft experiencing acoustic fatigue like you mentioned, or a CNC spindle trying to maintain a 1-micron tolerance.
Or even just an engine mount in a heavy-duty diesel truck.
Right, exactly.
Yeah.
Unwanted vibration leads to fatigue, it causes noise, and eventually catastrophic failure. And the real challenge that you face as an engineer isn't just knowing the physics, right? It's figuring out how to model all that chaos mathematically without just getting entirely bogged down by a million different variables.
Because when you look at high-speed footage of a vibrating engine block or a rocket payload, it doesn't look mathematically elegant.
No, it looks violent.
Yeah, it looks entirely random. So as an engineer, where do you even start? I mean, you can't model every single atom of the metal.
You really can't.
Yeah.
So you start by reducing the chaos to its most fundamental deterministic baseline. You have to assume a single degree of freedom first. And we model the fundamental equation of free vibration with viscous damping. And that involves 3 primary elements. You've got mass, spray, and damper. Those 3 elements literally form the foundation of every single complex model we build.
Let's translate that baseline equation into physical reality for the listeners, because the formula we always see in the textbooks is m times x double dot plus c times x dot plus k times x equals 0.
Right. And it's crucial to understand what those dots, the derivatives, actually represent in the physical world.
Yeah, break that down for us.
So the first term, m times x double dot, that is your inertial force. The double dot means the second derivative of displacement, which is
acceleration.
Exactly, acceleration. So we are looking at mass times acceleration. This is purely Newton's second law, F equals ma. It is the force that the mass exerts to just, resist any change in its velocity.
And what engineers constantly get wrong here, particularly when they are relying entirely on CAD software, is assuming they actually know their M value.
Oh, man. CAD lies.
CAD totally lies. It will tell you the mass of your machined aluminum block down to the gram. But out on the assembly floor, they add wiring harnesses, thermal blankets, half a pound of epoxy.
And suddenly your perfectly calculated inertial force is entirely wrong.
Exactly.
Which throws off your entire frequency calculation before you even turn the machine on.
Yeah.
But assuming you actually have your mass correct for a second, that mass is fighting against the next term in the equation, which is c times x dot.
Okay, so x dot is the first derivative of displacement, which means velocity.
Right, so this is your viscous damping force, and it depends entirely on how fast the mass is moving.
Not where it is in space, but how fast it's actively moving through space.
Yes, that distinction is huge. If the system is paused at the very bottom of its travel, right, even if the spring is fully compressed and screaming to get back to 0, the velocity in that exact millisecond is 0.
Which means the damping force is 0.
Exactly. That physical reality is essential. Viscous damping is the mechanism by which kinetic energy is bled out of the system. Usually, you're forcing a fluid through a tiny orifice, right? Which converts the kinetic energy into heat.
Like the shock absorbers in your car hitting a pothole.
Perfect example.
Right.
And finally, you have the K times X term. K is the stiffness of your spring, and X is simply the physical displacement from its resting equilibrium.
So the spring is completely blind to velocity.
Totally blind.
It only knows how far it has been stretched or squished. It's the restoring force that is constantly trying to snap the mass back to 0.
Right. And we set all 3 of these terms equal to 0 because we are modeling free vibration.
Meaning we aren't constantly shaking it.
Right. We kick the system once, we remove our foot, And we just watch the inertia, the damping, and the stiffness fight it out until the system comes to a rest.
But I feel like we need to pause and look at the massive assumption we're making when we say K times X.
Oh, the linear spring assumption.
Yeah. We are assuming a perfectly linear spring. We are assuming that if, 1 millimeter of compression takes 10 newtons of force, then 10 millimeters of compression takes exactly 100 newtons.
Which is a lovely, lovely textbook fantasy.
It really is.
Completely. Because in the field, especially when you are using polymer mounts, rubber isolators, or air springs, the stiffness is highly nonlinear. As you compress a rubber mount, it physically bulges outward. The molecular chains inside it align, and it gets exponentially stiffer.
So the K value just spikes.
It spikes hard. If your system bottoms out against a hard stop, your K basically goes to infinity.
And if K goes to infinity, your differential equation basically explodes.
Right. But we start with the linear assumption just to get a foothold in the math. So we have mass, damping, and stiffness. We know how they interact in a vacuum, but how do we tune them?
Yeah.
This brings us into the territory of resonance and critical damping, because a system without damping will theoretically just oscillate forever. It'll just endlessly trade potential energy in the spring for kinetic energy in the mass.
So to stop that oscillation, we have to look at the undamped natural frequency, which we usually call omega n.
Yes, and the math for this is straightforward, but really profound. Omega n is simply the square root of the stiffness divided by the mass.
That is basically the eternal seesaw of mechanical design, isn't it?
It really is.
If you want to raise the natural frequency, like make it vibrate faster, you increase the stiffness. If you want to lower the frequency, you increase the mass.
And that frequency is the heartbeat of your system. But you have to control it. You need to know the exact amount of damping required to stop the system from bouncing without making it overly sluggish.
Right.
We define this threshold as critical damping. Mathematically, critical damping is 2 times the square root of the stiffness multiplied by the mass.
So if I have a system at exactly critical damping, I pull the mass down, I let it go, and it just returns to zero perfectly in one smooth motion.
Exactly. No overshoot, no bouncing.
Okay, so we use that critical value as a benchmark to create a dimensionless ratio, right?
Yeah.
The zeta ratio.
Yes. Zeta is simply your actual physical damping coefficient divided by that theoretical critical damping value.
So logically, if damping stops the shaking and I'm designing a super high-speed CNC milling machine, I should just pack it with dampers, right? Make zeta greater than 1. Just over-damp the living daylights out of it so it never vibrates.
That intuition makes total sense until you look at the physical consequence of overdamping.
Which is what?
Well, if zeta is greater than 1, the damping force is so incredibly high that it actively fights the spring's attempt to pull the mass back to the center.
Oh, it's like a heavy industrial hydraulic door closer on a really cold winter morning.
That is exactly what it's like.
You open the door, let it go, and it takes 3 agonizing minutes to actually close.
And in your CNC machine example, if the tool head is overdamped, sure, it won't vibrate. But it will be so sluggish responding to servo commands that it will physically round off the sharp corners in the metal you're trying to cut.
Wow.
So in almost all mechanical isolation scenarios, you actually want a zeta value of less than 1. You want an underdamped system.
Even though an underdamped system will technically overshoot the 0 point and bounce a little bit?
Yes, because it settles back to equilibrium drastically faster than an overdamped system does. You accept a few micro bounces to maintain a fast response time. But you really have to manage that zeta value carefully.
Because if your damping is too low...
If it's too low, you run headfirst into resonance.
Resonance. The graveyard of poorly designed machinery.
Literally.
We've been talking about free vibration so far, just kicking the system once. But resonance happens during forced excitation, right?
When you introduce a continuous alternating force, like an unbalanced motor spinning or a rocket engine producing a pulsing thrust, you're actively forcing the system. And if the frequency of that forcing excitation perfectly matches the undamped natural frequency of your system, resonance.
You have achieved resonance. For the aerospace folks listening, the classic nightmare here isn't just the Tacoma Narrows Bridge blowing in the wind. It's the pogo oscillation on the Saturn V rockets.
Oh, the pogo effect, a terrifying piece of engineering history.
Right. The longitudinal vibration of the rocket structure itself perfectly matched the resonant frequency of the fuel lines.
Yeah.
So the vibration caused the fuel pressure to fluctuate, which then caused the engine thrust to fluctuate, which fed right back into vibrating the structure even harder.
It was a perfect, completely destructive, positive feedback loop. And if you look at the transmissibility equation, which calculates how much of the input vibration actually makes it through to the main mass if you have zero damping and you hit resonance,
Yeah.
the denominator of the equation literally goes to zero.
Meaning the amplitude of the vibration mathematically approaches infinity.
Right. The math dictates infinity,
Mm.
but physics dictates a catastrophic structural failure long before that.
Yeah, the metal just tears apart.
Exactly. The only thing preventing the machine from tearing itself apart at resonance is your damping, your zeta.
Mm-hmm.
And engineers measure the sharpness of this resonant spike using the Q factor, or quality factor.
Right.
For a lightly damped system, Q is roughly equal to 1 divided by 2 times zeta.
Which means if you have a very small amount of damping, a tiny zeta, you end up dividing by a tiny fraction, so you get a massive Q factor.
Exactly. A huge, violent spike in amplitude, the millisecond that motor hits the resonant RPM.
So the critical task in the testing phase has to be finding out exactly what your damping ratio actually is in the real world. You can't just trust the fluid specifications on the damper's datasheet.
No, never trust the datasheet. You have to measure it physically using a principle called logarithmic decrement.
Okay, so how does that actually play out in a testing lab? Say you have a prototype engine mount bolted to a test stand.
Yeah.
How are you pulling a dimensionless ratio out of a literal physical block of rubber?
Well, you attach high-resolution accelerometers to the mass, and you just hit it.
With a hammer.
Literally an impact hammer. You induce a shock and record the free vibration decay trace on an oscilloscope or a data acquisition system. What you'll see is a classic decaying sine wave, a series of peaks that get progressively smaller and smaller as the kinetic energy dissipates into heat.
And the logarithmic decrement is calculated by taking the natural logarithm of the ratio of the amplitude of any two successive peaks.
Exactly, and the reason we use the natural logarithm there is that viscous damping decay is an exponential function. By taking the natural log of that peak-to-peak ratio, you effectively linearize the math.
Wow.
Yeah. From that single, simple hammer strike test, the decay curve allows you to extract the exact physical zeta of the system.
Okay, so if I have a single mass on a single spring, I can find the frequency, I can test the damping, and I can theoretically avoid resonance.
Yeah.
But that's a toy model. Real industrial systems are multi-mass, multi-degree of freedom nightmares.
Oh, absolutely.
I mean, imagine a 6-axis robotic manufacturing arm. You have servo motors bolted to cast aluminum arms, which are bolted to other arms, all with their own stiffness and their own damping, moving simultaneously in three-dimensional space.
If you try to analyze a robotic arm like that, using classical Newtonian mechanics, drawing free body diagrams for every single linkage, tracking every single force vector in the X, Y, and Z axis simultaneously, you will just drown in the math.
Yeah, I'd imagine.
The trigonometric projections alone for a rotating, translating mass will cause a cascading error in your calculations. It's just unmanageable.
Which is exactly why the sources introduced the Lagrangian method. It just completely abandons the idea of tracking physical force vectors altogether.
The Lagrangian equation is arguably one of the most elegant mathematical escapes in all of engineering physics. It's beautiful. Instead of looking at force vectors pushing and pulling, Lagrangian mechanics looks purely at the overall energy budget of the system. It fundamentally asks you to weigh two things against each other: the kinetic energy actively moving in the system versus the potential energy currently stored in the system.
To give the listeners a tangible way to picture this, I like to think about trying to audit a massive multinational corporation. The Newtonian method is like trying to track every single penny. You are tracking every paperclip purchased, every coffee reimbursed, every microscopic transaction across 10,000 employees. It is exhausting. And if you miss one single receipt, your whole ledger is wrong.
That is a brilliant analogy. The Lagrangian method, on the other hand, is like acting as the chief financial officer. You don't care about the paper clips.
Exactly.
You look at the macro accounts. You calculate the total liquid cash moving through the business. That's your kinetic energy. Then you calculate the total assets sitting in the bank. And in real estate, that's your potential energy.
And you just plug those two massive energy totals into the Lagrangian equation. You take the partial derivatives of those energies based on how the system is moving over time, and the calculus inherently balances the books for you.
It really does. It spits out the exact differential equations of motion without you ever having to draw a single arrow on a free body diagram.
It feels like cheating, honestly.
It does. What makes this so powerful for complex machinery is the use of generalized coordinates. In Newtonian physics, you are permanently locked into the Cartesian grid, X, Y, and Z. But in a complex machine, Parts don't actually move freely in all directions.
Right, they're constrained by hinges and bearings and guide rails.
Exactly. If you have a pendulum swinging on a rigid rod, it's moving in X and Y simultaneously, right? But those movements are locked together by the length of the rod. They aren't actually independent.
So instead of tracking X and Y separately and constantly having to calculate the trigonometric relationship between them, Lagrangian mechanics lets you just define a generalized coordinate.
Yes. For the pendulum, the only truly independent variable is the angle of the swing. You assign a single coordinate to that angle. If you have a complex flight simulator platform sitting on hydraulic actuators, you look at how many independent ways it can move its actual degrees of freedom, and you assign one generalized coordinate to each.
Then you write one master equation for the total kinetic energy of everything moving, using the masses and velocities. You write a second master equation for the total potential energy, using the spring stiffnesses and the displacements.
And then the Lagrangian operator grinds those two energy formulas together and perfectly extracts the equations of motion for every single degree of freedom. It's magic.
But, and there is a big, but here is the critical vulnerability in the Lagrangian escape hatch.
Oh, there always is.
The math is flawless, sure, but it demands absolute perfection in your inputs. To calculate the kinetic energy, you need to know the exact mass and the exact moment of inertia of every single moving part.
And as we established earlier, CAD lies. The computer assumes your cast iron engine block has perfect, uniform density. It assumes there are 0 microscopic air voids from the casting process.
It assumes the machinist didn't accidentally leave an extra millimeter of material on one flange because they misread the tolerance sheet.
Exactly. And when you are trying to isolate a highly sensitive system, those tiny asymmetries matter immensely. An offset center of gravity by just a few millimeters will completely change how the system couples into rotational vibration.
So this is why theoretical math eventually has to give way to physical, experimental determination of mass properties.
You have to put the hardware on the bench and literally interrogate it.
Okay, let's walk through the physical realities of that testing laboratory. First, finding the true center of gravity, the CG.
The most robust method for heavy, complex, rigid bodies is the 3-scale method. You take your oddly shaped part, let's say it's that bespoke satellite chassis we talked about, and you lower it onto a rigid platform that is supported by 3 highly calibrated load cells or scales.
The total mass is just the sum of the 3 readings. Simple enough. But finding the physical location of the center of gravity requires balancing the static moments.
Right, because you know the exact geometry of where the 3 scales are positioned relative to each other.
Right.
You just look at the force distribution. If the scale on the front left is reading, say, 40% higher than the other two, the physical center of gravity is geometrically biased toward that specific scale.
Okay, yeah.
By setting the sum of the moments equal to 0 in your equations, you can pinpoint the exact X and Y coordinates of the CG.
So finding the CG is basically just advanced seesaw math. But finding the moment of inertia is where the lab gets really complicated. Because moment of inertia isn't about where the mass is, it's about how that mass resists being spun.
Exactly.
A heavy weight concentrated right at the center spins easily, but that same heavy weight spread out on the outer edges resists spinning violently.
Like a figure skater pulling their arms in to spin faster.
That's a thick visual.
To measure this experimentally for an object, engineers rely on the trifilar pendulum. Trifilar simply meaning 3 threads. It is a highly sensitive testing apparatus consisting of a lightweight platform suspended from a super-rigid ceiling structure by 3 flexible wires.
And these wires have to be of exactly equal length, spaced equally around the center.
Right. So you take your expensive satellite chassis and you carefully place it on the platform so that its newly discovered center of gravity is perfectly, flawlessly aligned with the exact center of those 3 wires.
And
then you introduce a very slight rotational displacement. You literally just twist the platform a few degrees around its vertical axis and let it go.
so the platform will undergo a torsional oscillation, just twisting back and forth, back and forth.
Yep. And you use optical sensors, or honestly just a highly precise timer, to measure the period of that oscillation, which we call tau in the math. That is the time it takes to complete one full twisting swing and return to the start.
Okay, and the math for the moment of inertia revolves entirely around that swinging period.
Completely. The moment of inertia is equal to the mass, times gravity, times the square of the radial distance to the wires, times the square of your measured period tau, all divided by 4 times pi squared times the length of the wires.
Which sounds intense, but it really relies on the pure physics of a pendulum. But the physical reality of running a trifilar test seems incredibly frustrating.
Oh, it's a nightmare.
Yeah.
Because the math assumes the wires have zero mass and perfectly uniform tension.
It also assumes you are testing in a vacuum. If the HVAC system in the laboratory kicks on, the air currents hitting a large asymmetrical satellite chassis will act like aerodynamic drag,
Yes.
which introduces a parasitic damping force that completely corrupts your measurement of the period tau.
Or, heaven forbid, if your wires are made of a material that stretches even a fraction of a millimeter under the heavy load, the length variable in your equation is suddenly wrong. And worse, the platform will introduce a slight rocking motion, so a pendulum swing, coupled with the torsional twist that just ruins the data completely.
Wow. But I'll push back on the scale of this test for a second. The trifilar pendulum works great for a satellite chassis or a drone payload. What happens when your rigid body is like a 10-ton steam turbine rotor or the massive crankshaft for a marine diesel engine? You cannot hang 10 tons of steel from 3 piano wires and give it a gentle twist.
You absolutely cannot, which is exactly why heavy industry uses balancing machines. These are massive, incredibly rigid lathes equipped with high-fidelity force transducers.
Okay.
When you are dealing with a rotor of that immense size, you aren't just looking for the moment of inertia, you are desperate to find the products of inertia.
Right, because products of inertia define the asymmetry. They tell you how the mass is unevenly distributed across different planes along the length of the rotor.
Right, so you load the massive rotor into the heavy-duty bearings of the balancing machine. You spin it up to a constant angular velocity, and even though it is spinning at a perfectly steady RPM, any asymmetric mass distribution will generate massive centrifugal forces.
Forces that just hammer dynamically against the bearings.
It's the exact same physics as a car tire that is thrown a small wheel weight. At 50 miles an hour, the steering wheel is perfectly fine. But at 65 miles an hour, the asymmetric mass generates a centrifugal force that literally shakes the entire front end of the car.
Just a vibrating nightmare.
Yeah.
Yep.
In the balancing machine, the load cells mounted on the bearings measure the exact magnitude and phase angle of those dynamic reaction forces. Because you know the rotational speed and you're capturing the exact force vectors pounding on the bearings, matrix algebra allows you to back-calculate the exact products of inertia.
So you mathematically map out the internal imbalances of the steel itself.
Exactly. You find exactly where it's heavy.
Okay, so we've characterized the monster. We've found the true mass, the exact center of gravity, the moment of inertia, and the products of inertia. We know exactly how this complex, rigid body will behave in a vacuum.
We have all the data.
But knowing all of that is totally useless if we just take this expensive machine and bolt it directly to a steel floor. We have to mount it. We have to actually design the master blueprint for isolation.
And this is where we transition from purely analysis to actual mechanical design. We are talking about resilient supports and the critical goal of decoupling the modes of vibration.
Decoupling.
Yeah, to understand decoupling, we really have to look at how different types of motion contaminate each other, which we call modal coupling.
Let's visualize modal coupling for everyone. Imagine you have a heavy rectangular air compressor sitting on 4 soft rubber mounts on a factory floor. The center of gravity of the compressor is pretty high up near the heavy motor, well above where the rubber mounts actually attach to the base.
So if a shock wave comes from the side, a lateral force in the x direction, the air compressor doesn't just slide cleanly in the x direction. Because that center of gravity is elevated above the mounts, that lateral force creates a moment arm.
It creates torque.
It creates torque. The translational force in the x direction causes the entire machine to pitch and roll. The translation is tightly coupled to the rotation.
And that coupling is a total nightmare for predicting maximum displacements. Because if your machine is twisting and rolling unpredictably, it might literally smash into the protective casing around it.
Or if you have delicate plumbing attached to the compressor, that twisting motion will fatigue and eventually snap the pipes.
Let's elevate the analogy, like the waiter on a cruise ship analogy, to something more industrial. Think of a heavy lift drone carrying a really expensive camera gimbal.
Okay, I like that.
If the payload is slung underneath the frame and the center of gravity is offset, every time the drone accelerates forward, the payload swings and tilts back. The forward thrust is intimately coupled to a pitching rotation.
But if you could design the mounting system so that the elastic center of the mounts perfectly aligns with the physical center of gravity of the payload, you completely decouple the system.
Meaning the drone accelerates forward, and the payload translates forward perfectly horizontally without tilting a single degree.
Exactly. So how do we actually achieve that equivalent center of gravity system in heavy machinery?
Mm.
We can't always just magically move the physical mounts up into the middle of the engine block. The mounts usually have to sit at the base.
Right. Gravity dictates they go on the bottom.
The physical solution is to incline the resilient supports. Instead of placing your rubber isolators flat on the ground, you tilt them at a specific angle, pointing them inward toward the center of gravity.
This is the magic angle, denoted in the math as phi prime. But I want to spend a moment on the physical mechanism here because it's fascinating. Why does tilting a piece of rubber stop a machine from rotating?
Because it actively manipulates the stiffness matrix of the system. See, an isolator has different stiffnesses depending on how you push it. It has a compression stiffness when you squash it flat, and a shear stiffness when you try to slide the top horizontally across the bottom.
So by tilting the mount at the angle phi prime, you are literally projecting those stiffness vectors up into the center of the machine. You are creating a virtual geometric focal point.
That's exactly it. When that lateral force hits the machine, the tilted mounts resist with a precise, engineered combination of compression on one side and shear on the other.
Wow.
This angled resistance generates a counter-torque that perfectly instantly cancels out the overturning moment caused by the high center of gravity. You have literally engineered the rotational coupling right out of the system.
And the math for finding that perfect angle is brutal. It's a massive trigonometric equation setting the physical locations of your mounts against the ratio of the compression stiffness to the shear stiffness of your specific rubber compound, all wrapped up in a bunch of cotangents.
Oh, the cotangents are awful. If you look at the stiffness matrix for a coupled system, you have all these off-diagonal terms. These terms are the mathematical representation of the coupling. For example, a non-zero kxy term means a force in x physically creates a displacement in y.
Right.
But when you tilt the mounts to the exact angle phi prime, the math dictates that those off-diagonal terms physically drop to zero. The matrix becomes perfectly diagonalized.
But sitting at a desk and grinding out cotangent formulas for every possible mounting configuration is incredibly tedious, especially if you are constantly changing the rubber compounds during the prototyping phase.
Which is exactly why the engineering community developed space plots. Long before instantaneous matrix-solving software was available, engineers needed a graphical way to optimize these mount locations quickly. A space plot is a dimensionless graph based on the radius of gyration of your specific machine.
So you take your rigid body, calculate its radius of gyration, and literally map it onto this pre-calculated grid.
Yep. The grid is overlaid with these beautiful families of curves, ellipses, and hyperbolas that represent the natural frequencies of the system at various mounting angles and stiffness ratios.
So by finding where your desired mounting points intersect these curves, you can visually read the resulting decoupled natural frequencies.
It completely turns a massive algebraic headache into a visual optimization puzzle. You can instantly see that if you just move the mount 2 inches to the left, you jump to an entirely different frequency curve. It is a brilliant way to maintain physical intuition over the design rather than just blindly plugging numbers into a black box solver.
And achieving this decoupling is never more critical than when a system is subjected to velocity shock.
Oh, velocity shock, the ultimate test of isolation.
Right, because velocity shock isn't a continuous vibration, it is a sudden, instantaneous change in the foundation's velocity. The classic example is a shipping container full of super-sensitive electronics being lowered by a dock crane. The crane operator drops it too fast and it slams onto the concrete dock.
So the concrete foundation's velocity goes to absolute zero in a millisecond. But the electronics suspended inside the chassis still possess all of that downward kinetic energy, and they want to keep traveling downward at 3 meters per second.
That kinetic energy has to be entirely absorbed by the resilient mounts in just a fraction of a second.
If your mounts are placed arbitrarily and the modes are heavily coupled, that massive downward shock will instantly convert into violent twisting, rolling, and pitching.
The internal components will experience a chaotic combination of g-forces from multiple directions simultaneously.
Tearing wiring harnesses, shattering printed circuit boards, it is almost mathematically impossible to predict the exact peak acceleration in that chaotic scenario.
But if you used your space plots and you tilted your mounts to phi prime, and you perfectly achieved an equivalent center of gravity system,
then the complex math completely collapses into beautiful simplicity. Because the system is completely decoupled, a purely vertical velocity shock will only excite the purely vertical translational mode. The machine will just plunge straight down into the mounts and spring straight back up with absolutely zero rotation.
And because it's now acting like a simple single degree of freedom system, you can pull out that very first equation we talked about today. You can calculate the exact maximum displacement the mounts will endure, and you can calculate the absolute peak G-force that the electronics will actually experience.
You engineer the uncertainty right out of the system. With absolute mathematical certainty, whether the optics on that massive, expensive satellite will actually survive the drop.
And that is the whole point. We don't do this math to pass a university exam. We do this math so things don't literally shatter when the real world hits them.
But there is a whole frontier beyond this.
Mm.
Everything we have mapped out today, springs, the dampers, the magic angles, it all relies on passive isolation.
Right.
We are tuning static physical properties before the machine is even turned on, basically just hoping our estimates of the worst-case scenario were accurate.
So you are building a very clever but ultimately static cage.
Exactly. The future of this field is active vibration control. We are moving towards smart materials. Imagine magnetorheological fluids in your dampers that can instantly change their viscosity, their C value, when exposed to an electromagnetic field.
Oh, wow.
Or imagine piezoelectric actuators in your mounts that can actively change the stiffness, the K value, thousands of times a second.
So instead of trying to perfectly tune the natural frequency ahead of time to avoid resonance, the system is actively reading the incoming vibration from the environment and instantly shifting its own natural frequency to dodge it.
It creates a system that isn't just resilient, it is highly reactive. The master blueprint of the future won't just sit there blindly absorbing shock, it'll actively fight back.
Remember, design junkies. Some problems you attack head on, some problems you walk around. The wise engineer knows the difference. Knowledge and wisdom are not the same thing. Knowledge is the information you hold, and wisdom is knowing how to use it properly. Strategy without tactics is the slowest route to victory. Tactics without strategy is the noise before defeat.